Okay, so let's go. So, introduction to policy-based methods. So, why do we need this new method if the previous uh, algorithms based on value-based methods were working so well? And we will also see what the difference is between value-based methods and policy-based methods. Apart from the obvious difference in the name, uh, that values-based methods are based on action value, whereas uh, policy-based methods are based on policy. So let's see that. So what were we doing previously? We were in value-based methods. There was an environment, and we used to interact with the environment, collect some rewards, add them to this Q table, if you remember the very famous Q table, and use this Q table to uh, determine an optimal value function Q star. And once we have this optimal value function Q star, uh, we could determine the optimal policy given this optimal value function. So this was for a discrete environment with discrete state spaces, limited number of states, and some actions, and this was it. What about for continuous state spaces? Given a state, there are again it's called continuous because there are many like infinite states possible for continuous state spaces. Now what you see here is these four variables make up one state. So a particular combination of these four variables makes up one state, and since the range of values of each of these variables is continuous, it's the values are in range. So there could be millions and millions of combinations of these four variables, and so there will be many states, and that's why it's continuous state space. So what we did in value based methods, given a state, and when there is a continuous state space, we had to use a neural network as the function approximator of value function. So as compared to discrete state space where we just use the table to compute optimal value function, we used a neural network to compute the optimal value function in continuous state spaces. So given a state and our value function, we compute action value for each action, right? And so, and based on that action value for each action, we chose which action to state. If we had a greedy policy, we use the best action. If we had epsilon greedy policy, we randomly chose one of these actions based on the value of epsilon. So we randomly chose either of them, or we chose a greedy value. We chose the action with best action value based on the value of epsilon. Again, epsilon greedy. That's what the epsilon greedy policy is. So in both of these methods, the common thing is that we had to compute a value function first, whether it's discrete or continuous state space. Uh, Even here, this neural network, you can say that this neural network is a value function, right? Because it has these parameters theta. Given a state, they generate action value, so it's also an action value function. So the common thing was that we first had to compute an action value function, and then that action value function will give us action value of each action, and then we chose the policy. So this was the intermediate step. in value based methods, and it worked well. As many of you have completed the navigation project, um, some of you are still working on it. That's fine. So I encourage you to finish it quickly so you can catch up. Um, so if the value based methods were working so well, why do we need policy based methods again? What difference does it make to just remove the intermediate step? Because many of you have guessed by now that difference between value based methods and policy based methods is that we just don't have this intermediate step. We directly go to the policy, the optimal policy. We directly go and compute this optimal policy um, in value in policy based methods. So what difference, why does it improve it so much, and why give it a separate name, right? So there are few reasons. Number one is simplicity. You will find out soon why simplicity, because we we avoid computing obviously the action values. But why does it, but it saves us some time and some computing as well. It makes the code simple. Instead of going through many steps, we directly jump to computing policy, so it makes things simple. Okay, you will find this out soon. And number two is stochastic policy is possible. So if you see in the previous example, this is a deterministic policy, right? You you only choose one action here. There is no probability of choosing both actions here. You only choose one action. Either uh, you choose the best action or you choose the worst action depending on your policy, but you choose only one action for sure. There is no probability. So policy based methods allow for a stochastic policy. Okay, you can there will be a probability of selecting either of the actions. Number three is continuous action spaces are also possible. So until now you saw state spaces were continuous, but in real life problems, you will see that even the action spaces are continuous. And policy based methods allow for solving those kind of tasks, those kind of environments. So we'll see. So these are the three main points, main reasons why policy based methods are used. So is it possible to directly determine the optimal policy, and how do we do that? So let's take a look. If we use a neural network again, same environment, same task. We use neural network, and given a state, it gives out probabilities of two actions this time, right? So instead of giving out uh, the action value of each action, it gives out probability. Now you will say that, so what's the big deal? What's the difference? Uh, previously when we computed action values, we didn't use any activation function in the output layer, right? If you remember from your DQN exercise and your project, in your network for computing action values, you didn't use any activation function in the output layer, and you took whatever value it gave as the action value. So you will say that, okay, so you just added a softmax function to this output layer, right? And it gives you softmax or sigmoid function, and it gives you probabilities. So what changed? What's the big deal? And then you will say that, oh, okay, then I will just choose the action which has highest probability. Again, it is the same thing. So no, there is a difference here. So the difference is that, so first of all, I will cover again. There is no activation function in the output layer, and we used argmax to determine the best action. Uh, Here, stochastic as well as deterministic policy is possible. Use softmax or sigmoid in the output layer, and if to get stochastic policy is that any action could be chosen randomly. So you sample one of the two actions. So in your instead of using argmax in your code, after getting this out final layer, you use random dot choice, right? And you randomly choose one of these. So that makes possible having a stochastic policy. To have a deterministic policy, don't sample, don't use a random dot choice. um, just use the action which has higher probability. So that makes it deterministic. So policy based method not only has extra stochastic policy, and as you will see later on, continuous action spaces possible, but also allows for having deterministic policy. So coming back to my point, that what changed, what's the big deal, just added softmax here, right? And I'm still selecting the action which has higher probability here. Previously what I did is just selected the action which has higher action value. So what changed besides just the name and the final output function? So the thing is that here the agent or the network doesn't care about the action value. So now you're seeing that this action has higher probability here, this action has a lower probability, but this action might have low action value and still have higher probability. So that's the difference. Just because this action has 90% and this has 10% probability doesn't mean that this action has higher action value. Okay, now this instance, this what we are seeing here is just one time step in a particular episode, if it's an episodic task, or if it's a continuous task, then it's continuous. So this is just one time step that we are seeing here. So for a particular time step, the agent might choose to take action which has low action value in a time step, but the agent thinks that eventually choosing this action will lead to higher expected return in the end, right? So the main objective of any of these algorithms is that to improve the expected return of the agent, right? So when we used value based methods, we said that okay, always choose the best action, collect max reward always, and then eventually you'll have highest return possible, because you are always choosing action which has highest value. But that might not be possible, that might not be the case, because the agent might select an action which has low action value but high probability. It's choosing the action because it has higher probability. The agent has assigned higher probability to this action for some reason, but that reason doesn't have to be higher action value, right? So I'm trying to separate action value from probability here. Just because the agent gives 90% probability to selecting this action doesn't mean this action has higher action value. In this time step, the agent might select to take this action even if it has low action value, because the agent believes that eventually taking this action will lead to higher return in the end. So it's just like the, if you remember the exploration versus exploitation problem, that there were two doors, and you keep selecting one door which gives max return, and you have some return. But if you had chosen some other door, it might give you low return, low reward at first, but eventually you might win a lot in the end, right? So that's what happening here. The agent doesn't care about action value at all. It just cares about the final expected return that it will make, and it just want to maximize that return. So to maximize the final return, it assigns probabilities to actions in each time step, and these probabilities uh, are independent of the action value. The agent, the neural network, the agent just assigns some probabilities to actions which it thinks will lead to higher expected return in the end. Okay, so the policy based methods separates action values from actions here. Okay, actions are chosen based on uh, the whole outcome of the task. Probabilities are assigned to actions based on probabilities to are assigned to actions in each time step based on the final outcome, the final total expected return, and the objective is to maximize their expected return. So the agent will uh, choose actions which will eventually lead to max return. The agent might choose give high probability to action which has low action value, uh, but the agent doesn't care about action value again, right? There is no care, no emphasis, no burden given to action value at all. We just get probabilities assigned to actions based on what the final outcome will be, and our objective is to maximize expected return in the end. So no caring about the action value here. And again, um, both stochastic and deterministic policies are possible, but also continuous action spaces are possible. So this is just an example of one of the OpenAI gyms environments, bipedal walker environment. So one second. Yeah. So what happens here is in this environment, and you can check out this PDF where they have solved this environment, and you can check out OpenAI Gym's GitHub page or website to see more details about this bipedal walker environment. Okay. Uh, so so what is this? So there is an environment. This walker is walking, and there are different kinds of hurdles, and the walker has to overcome these hurdles. Sometimes jump, sometimes climb. Sometimes go over this D type of hurdle. Different kinds of hurdles, and the walker has to maximize his reward as always in the end. Uh, and how does it move? So it has these four parameters to to control how much force is applied to its hips. So how does it move forward? Torque. Okay, there are two hip joints, and how much force is applied to its knees. Okay, so this might be for many reasons. Uh, how we use our knees, how we use our hips to move forward. We When we walk, even we apply some force to our knees and hips to move forward, right? So so one action of this agent is a combination of four values of these four parameters. So each parameter has a value range between -1 and +1. Okay, and the agent will select one uh, value between this range, and one action of this agent at one time step will be a combination of these four numbers. So even here, just as the state space is continuous, the action space is also continuous, as you can see. So policy based methods make this possible. Now we'll make a comparison, like how it was not possible with value based methods. uh, you know you there is no at any at every for every state at each time step you have to get in this in bimetal case you have to get four values between -1 to +1. But how do you know that has they are maximizing your action value? It makes a bit complicated. How do you know this four will maximize your action value? Even if you use value based methods and you use some activation function here, and by now many of you have guessed that we will have to use tanh function to get a range between -1 to +1. We have seen previously in some lessons, previous lessons, to get a range between -1 to 1. And also I discussed in the neural network webinar. You can check out that webinar on neural networks. It is in I have pinned it in the Slack channel. So we saw there that to get a range between -1 to 1 you use tanh function. So some of you will say that I'll just use tanh function here. Suppose there are two actions. I'll use tanh function and it will give me a range. But how do you know it's maximizing the action value? It makes things very complicated. And for every combination, you will have to have a different action value, right? And it will be very, very computationally expensive to execute that, to compute the max action value at each time step. So instead of that, we will use tanh function here. Instead of caring at all about values, we will use tanh function, and the network will directly give out four values in our case here, and that four values together will be one action, and that will be the action of this agent at each time step. Very simple, no need to worry about any values. So simplicity again, and also possibility of having continuous action spaces. So again, um, you use softmax or sigmoid here. If you randomly sample, it's stochastic policy, right? So sometimes the agent might even choose a action with less probability, right? Because you're randomly choosing. So that's stochastic policy. Or deterministic, if you want to go with deterministic, choose the policy which has highest probability, right? And continuous action spaces are also possible with using tanh function, and it makes it very simple. If you use the same thing for value based methods, it's going to be very computationally very expensive. So that's the plus point of this. So how do we, given a state, given an environment, right, we have theta and we want to select these actions probabilities, or for continuous action spaces some combination. So how do we select this? How do we train our neural network theta to maximize our expected return in the end? So one of those methods is hill climbing. Actually, if you want to maximize return, it's hill climbing. And so the difference between hill climbing and gradient based methods is that they're exactly opposite, right? Hill climbing is exactly opposite of gradient based methods. uh, so in sorry, not gradient based methods, gradient descent, I'm extremely sorry. So hill climbing is exactly opposite of gradient descent, as you can also guess from its name. So in gradient descent, we optimize our theta, we change our theta parameters. Theta is all the parameters of this neural network. So we change or adjust or you know uh, change their values such a way, improve their values such a way that the loss is minimized. So that was, we took a gradient, that is the differentiation, the derivative of each of these weights, uh, with respect derivative of the loss with respect to each of these weights, and we tried to reduce the loss, change theta by reducing the loss. Here we want to increase, we want to maximize our return, so we change theta in such a way that it maximizes the return. So it's exactly opposite of gradient descent, hill climbing. Now I've written here black box optimization. So this hill climbing method is called black box optimization. Why? So because we know that if we change theta, it will change uh, j, right? So this is the connection. So we have a state, we have some value of theta, will give out actions. So that will be the policy. We will act this policy on the environment. Environment will give reward, and it will give j. So theta influences policy, policy influences reward, reward influences j. So we know that j is somehow related to theta. We don't know what the exact function is between j and theta, right? There is a direct link between theta and j only. There is nothing else in between. And we also don't care about what the exact relation is between j and theta. We just know that changing theta changes j. So what black box optimization does is it will tune, it will add some noise to theta and see how j changes, and then it will adjust theta this way. So let's take a look at the pseudocode of this one. Yeah, so let's see. Let's say that theta has only two bits, theta 0, theta 1, and there is this maximum return sitting somewhere here. This is if we draw a graph, it will be up, down, up, and up, slightly down, 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 down. So there are many local maximas here, and there is one global maxima. So you want to reach here. So the hill climbing, and hill climbing is also called gradient ascent, uh, which is exactly opposite of gradient descent. Uh, so this is just an illustration how um, changing theta will, at first there is some value of theta, and you get a return of 3. Then you make a slight random change to theta. It might go down to return 2, or it might go up. If it goes up, that means you are in right direction, right? Because you want to reach here. Again, you make some small random change. It will go to 6, return, change, and it will reach here eventually. So you change theta a bit and see how j changes. If j goes down, you discard that value of theta. If j goes up, then you add slight noise to that value of theta and see if j goes up even more. So it's just random noise, adding random noise to value of theta and see how j changes. Again, we don't know what this actual function is. We just know that j is function of theta. That's it. That's called black box optimization again. So yeah, this is the general hill climbing algorithm. um, Initialize the weights theta arbitrarily, collect an episode, record return g, right? So g is the return per episode. Call that theta as best theta and g as the best g. So we are setting benchmarks here. So this is the best until now. Okay. And then again come another episode. If g increases, then you set the new benchmark. If g doesn't increase, we keep the same benchmark. Same for theta. If g improved, you change the theta benchmark. If g doesn't improve, you keep the same benchmark as previously. So solve solve the episode, run as many as solve the environment, run as many as possible episodes until you get um, the best best G until the G uh, doesn't change much, until G maxes out, right? Sorry, the total return, yeah. So total return G until its maximum, you keep doing the same thing. So this is the loop. Add a little bit of random noise to this, the benchmark, to get new sets of theta new. Collect an episode with theta new, record the new G new. Improve. If G new is best, then theta best is the new theta new is the new theta best. So as I said here, same thing. And also previously I discussed, right? Add some noise, see if it goes up or down. If it goes up, save it. Add some noise mode, save it. If it goes up, save it. If it goes down, discard it. Add some other noise. So yeah, the same process. Now, what is the difference between G and J here? So here it's J, but here it's G. So it's simple difference. G is the return per episode, and each episode is different because of randomness. So G in one episode will be different than G in the other episode, right? But J is the actual expected return from many episodes that you collected. So it's like an average of the G's. You collect G in every environment, every episode, and it's going to be different. It might not be different, but it can be different due to randomness. And then you take average of all the G's you collected over all those episodes, and that's your J. uh, if you remember, when we solve our environments, we say that previous 100 episodes, average over previous 100 episodes. So J will be that average over last 100 episodes, and G will be that individual return from each episode. So that's the difference between G and J, and our objective is to maximize this return J. And when we say that the environment is solved, we say that J has crossed our expectation, right? When you solved your environments previously, when it passed, whatever the benchmark was for the environment, that was the max J expected from that environment, and you crossed it. That means you solved it. So that's the whole algorithm for hill climbing. Now there are some improvements done to hill climbing, because it's very possible to get stuck in local maxima, right? Because we are randomly changing weights. So what are these improvements? Let's take a look. Just 1 second. So what are these improvements? Because it's very possible to get stuck in local maxima, just like in gradient descent it was possible to get stuck in local minima, and there were improvements suggested to get out of local minima and go to global minima, right, when you reduce loss. Similarly, there are problems with local maxima as well, uh, and there are improvements suggested. So let's take a look at them. Number one is a steepest ascent hill climbing. So what is it? So this is like a top view of our hill here, uh, and these are contours, right? So as this the small contours are where there is a where the height increases. If there are bigger contours, that means it's a lower height. Yeah. So what are the stars? So what we say is that, suppose our arbitrary initial value of theta starts here, and we get some return, right? And it's going to be low because it's in this bigger contour, right? We want to reach smaller contour here, smaller oval here. So we start from the bigger contour, it gives some return, and then we add random noise to it and get some candidates. So these are 6 candidates. we added 6 different types of random noise to our actual arbitrary initial value, and we compute returns for all, and then we choose the maximum return, right? So instead of choosing this is the wrong direction, we will go down, the- and this goes directly towards the highest one. Even these are going high, even these are going high, but we use this. That's why it's called a steepest ascent, because we are just using that candidate of theta, uh, which gives the highest return of all these candidates. So it's steepest ascent. We are going up very fast, right? So that's one way. Another way is simulated annealing. So what the method here is, in, instead of just choosing small number of candidates, and you can draw like a circle here, so this is a smaller radius of noise. What's the best, sorry, what simulated annealing is that in the beginning you have a bigger radius of candidates, so you have many candidates, and as you go at many candidates, and then you compute the return and then choose the max one, only one max. And if you, if it's improving your return from this to this, that means you're going in right direction, so you will reduce your range of noise, you reduce the radius of your noise, as is done here. Again, you compute the returns for all of those in this other circle, and choose the best one, and again uh, choose the best one, and then reduce this radius of noise even more, even smaller radius of noise. And then next you will, you know, obviously this will be chosen, and then you again reduce the radius, so, and you reach your highest return. So you start from a bigger radius and then you go towards smaller radius. So it helps in bigger radius is good because it will help you avoid any uh, local maxima as well. There are more effective methods coming in later slides, but this is also one good way to avoid local maxima, because you know, if we if you start from here and there's a local maxima here, if you start from here and if you have smaller radius, you go up and you will reach here and you will stop there. But if you have a larger radius, instead of selecting some um, return, some theta with return from here, you might select a theta from return here, right? Because you, if you use large radius, and this might take you in the right direction. Again, it's probability, right? But yeah, so if you start from much larger radius and then go small, it's possible to avoid or skip this local maxima in the first place. So that's simulated annealing, higher radius and then small. uh, but what if, what if you do get stuck in local maxima? Now we saw here, as I said, suppose your first candidate, initial candidate, gives a return somewhere here, and then uh, you want to use a simulated annealing, right? And then you have a higher radius. But what if, due to some probability, the candidate with higher return is again selected from here instead of somewhere from here? Then you will reduce your radius. So if the radius is reduced, you are stuck. You will get stuck in this local maxima, this small hill, and you will keep reducing radius and you will reach here. And then you realize that this is not the max return that I can get, because the actual max return is here, right? So you're stuck in local maxima. So the to avoid, so if you're stuck in local maxima and if you want to get out of that, the method is adaptive noise scaling. So as this show here, higher radius at first, smaller, smaller, and they get to this local maxima, right? But then they increase the radius of this again, of this scaling, and then they realize that there is a higher point higher than this one actually. So that's adaptive noise scaling. So if you are stuck in local maxima, uh, and you will know that you are stuck in local maxima because you will know from the numbers that you are getting. uh, if the environment is getting solved at let's say plus 10, value of j is plus 10, and if your algorithm stops improving j after plus 2, that means you're stuck in local maxima, right? This is how you will know. So you want to reach plus 10 and even more, you are going to higher, because that's how the environment will be solved. So to get out of local maxima, you use adaptive noise scaling. So once you go to 2 and you are stuck there, you increase your radius even more, again very wide radius, and then see if you are getting any other higher value, and the same process again. If you get higher, then you again reduce the radius, make it small, small, small. If you are again stuck, increase the radius and see if there is any other higher value. So that's called adaptive noise scaling. uh, Adaptive noise scaling, as the name defines it. Okay, now these first three methods we saw, they had a candidate, initial candidate, and then we added random noise with radius, and then we just chose one of those theta candidates, and all these candidates were discarded. Their value, the information we get from them was not used. Same goes for this one. We just choose the max. We have higher radius, we choose the max one, higher reduced radius, max, max, max. Only one candidate. Even here, you just choose only one candidate. But there are two ways to make this more efficient: cross entropy method, and then there is the evolution strategy method. So in cross entropy method, you don't throw away all the candidates. You have initial candidate, you have this noise, and then you select top 10 or 20%. So all these candidates, all these theta candidates will give you some value of return, and then you select top 10 or 20% returns, and then take average of those, and uh, take the average of the thetas that give you top 10 or 20% returns, and that will be your new theta. And then again uh, add noise to it again. Select thetas with top 10 or 20% return, take average of the thetas, that will be your new theta, right? So when you say selecting one policy, select 10, 20, and then take the average. So I'm taking average of the thetas, of the thetas that gave me top 10 or 20% return. Okay, theta, or the theta parameters, or the weights of the network. So that's cross entropy method. We only take 10 or 20% and take average. Evolution strategy uses all of them, so it is even more efficient. So cross entropy method was efficient because we didn't throw away all of them, we used some. Evolution strategy will use all of them, and we take weighted sum of them, weighted by the return they get. So again, this weighted sum is of the thetas. That's important to mention, because some people will think that it's a weighted sum of the returns. No, it's, so for each theta you get some return, right? So low return, low return, low return, high return, high return, high return. So for each theta, uh, uh, so each theta is multiplied by the weight of its return. So if you take total return, get a sum of returns, all these returns, and then divide each by the sum, so that gives you the weight of each, or weight of that theta. So weight of that theta times the theta, plus weight of this theta times the theta, and so on, so on, so on. Right? You know how the weighted sum works. So instead of throwing away even, you are throwing away 80% here, or 90%, you only using 10%. Instead of that, we are using all here and take weighted sum. And it's called evolution strategies because only the thetas that are best have higher say in improving the theta than the thetas which gave lower return. So it's just like how evolution happened, evolution of animals, evolution of genes, natural selection. Better best the ones that give better return are improved, have higher say, and the ones that give lower return, they have lower say in determining the theta. So I was also going to cover some code for this. I have some minutes, maybe I can cover this webinar. Yeah, so next week I will cover the reinforce algorithm coding in the reinforce in the second lesson, the policy gradient methods. Yeah, so I will do a walkthrough through that coding exercise of reinforce algorithm. Very important, very interesting as well. uh, this today's lesson took a bit of a time. I didn't think it will take so much time, but it was good to know all the basics. Basic difference, first of all, what is the basic difference between value based methods and policy based methods, and how we are separating policy from value. We don't care about value. We select policies, we select actions that might have low value in a certain time step, but eventually they will lead to higher return. That's the point of policy based methods. I have some 10 minutes, so I will go through some coding for hill climbing. So, 1 second. Yeah, so quickly, so this is the hill climbing exercise, hill climbing notebook. This is from here. So this is the lesson, introduction to policy based methods, and over here there is coding exercise, and many of you might have already gone through this. So I downloaded this coding exercise. Okay, so I'm going to cover this now. So hill climbing, basic idea you can read here. It's opposite of gradient descent and blah blah blah, adaptive noise scaling and etc. So they're using adaptive noise scaling here, right? All the libraries we imported, gym environment. So this is the policy class which will determine your actions, and we are not using any neural network here because it's just a simple demonstration. um, a an array of size state space by action space, and we randomly initialize them and randomly select their values from a uniform distribution between 0 and 1. uh, and then this is like softmax. This is the softmax function. Instead of using actual pytorch, we are using numpy. So this is like a softmax function. And then we select, if it's a deterministic policy, yeah, so we select argmax of probs that we get from here, from the when state is inputted here. Or if it's a stochastic policy, we will select random dot choice, as I said previously. Probability is probs, and it's so it's going to be either 0 or 1. So when this says 2, it's going to be either 0 or 1, and p will be selected from probs based on the probabilities, right? Random sampling. So we create an instance of policy. Obviously we make environment, set random seed, instances of policy. So this is the actual algorithm. uh, no big deal. So we set our best weight as our initial weight, policy.w, uh, attribute of policy weights. um, we act this way, this thing, select random, either random or deterministic from the probabilities. The environment will give out these values, and it will also give out rewards. We add up the rewards for each episode. We are running whole episode, and then we are adding up the rewards and we are discounting them, so discounted sum. And if the actual r is greater than equal to best r, so there is some, so this r from episode, and this is best r is set to minus infinity, so anything is better than minus infinity, so it will start from this, from the first episode itself. So if the r from this episode is greater than equal to best r, we set best r equals r, so we are changing the benchmark, improving the benchmark. And we set best w as policy.w, so we are also changing, setting the benchmark here. So this is the new benchmark and this is the new benchmark. And if they are best, then we add a small noise to it. So noise scale is decided here, what's the radius of noise that you want to add, right? So noise scale is the radius of noise, and here we add noise to it. Add noise to this weight. So we don't change the best w, we only change the policy.w, right? So this new weight will be used in next episode. And if it gives better r, then the best w will be made equal to that, made equal to this policy w. And if this doesn't give better r, then we do this. So else we again set noise scale, but this noise scale is bigger. So these are the two important steps. And this is adaptive noise scaling, right? So if we get r we get is better than our previous benchmark, we add a small noise to it. So noise scale is the smaller radius. If the r wasn't better than our benchmark best r, then we add a bigger noise to it. So this is the adaptive noise scaling. As we have seen, smaller, reduce the radius as long as you are getting better r. Once you get bad r, increase the radius. So the noise scale is the radius. And then we do this for many episodes. And that's it. That's the adaptive noise scaling way of hill climbing that's used here. So go through this, and please let me know if you have any questions, and on Slack anytime. uh, Quickly, CEM cross entropy methods. If you remember, we only use 10-20% and take average of the thetas that give top 10-20%. And all these things here, instead of using neural networks, since you are not using PyTorch and the optimizer, uh, we have used this here, right? So we are setting the weights so that we can change them later. We can add noise to it. This is just for adding noise manually to it instead of using the optimizer in PyTorch. Which does it, which changes theta automatically. So don't get scared by this. No big deal. You could use PyTorch here as well, but you'll have to make some changes to the algorithm other places. So the same thing. Uh, Evaluate, and yeah, elite fraction. So you are using 20%, top 20% here. So go through this. There is not enough time, but go through this. It's self-explanatory, not very scary algorithm, not very scary code. If you have any problems, just text me, direct message me on Slack, and I will get back to you. Okay. So that is it for today's webinar. um, Again, any questions, direct message me on Slack and I will get back to you as soon as possible. uh, if you are still working on some projects, also you can ask me right away and I will help you with those projects. So that's it from me. Thanks for watching this. Bye.